core group is here. Okay. Okay. Okay, maybe we'll spend 5 minutes watching some side videos, just that, and that will give people more time to come in today. So today, we are. So today the focus of discussion will be data mining, or more precisely spatial data mining. So we'll touch a little bit upon also spatial statistical background, but not in great depth, but focus primarily on the spatial data mining pattern families and approaches. And you can kind of see where. So in terms of resources, you have the PDF version of the slide. And here, at the end of the class, we'll look at the review quizzes. This is a nice survey paper, and a little bit old. So the talk, in some areas go beyond the paper, particularly for hotspot detection. Life. Many of you may have seen some of this, so if you know some examples, at least the ones in early part, you might know. And then the later part of video actually shows you a lot of spatial examples, which hopefully would be new. Okay? So let's maybe watch this short, about 5-6 minute video. And one quick show of hand, how many of us are new to data mining? Okay? And, all right, a few hands. Okay, so for people who are new to data mining, this may also be a small engagement thing. You can kind of see how it is impacting our lives. Even though the field started in late 90s, it's a very young field, but very quickly it started, affecting government, our commercial world and so on. And it's a very applied field, so it was always meant to solve problems at hand. Right? So it's not a surprise impact. It's an Australian video, so sometimes the language is a bit strong, so pardon that.
Tell them how much I earn, where I live, how many kids I have, what magazines I read, my deep sure, it's great to get advertising that's particularly relevant to you, but now that companies know more about you and your behaviour than you could possibly imagine, they target you when you're at your most vulnerable and open to suggestion. It's not that you're actually getting the best products, you're getting the best marketed products. Now what about if this company that has all your information sells it illegally like T-Mobile did in 2009 in the UK?
That sounds good. King ice cream! I'll see ya.
I think we lost him. In Europe, they're trying to fight back against this sort of thing with laws that force companies to tell you what data they're going to collect and what they want to do with it. But in Australia, you're pretty much on your own. So, if you don't want to be bombarded with personalised ads, well, don't sign up to loyalty programs, install track blocking software on your computer, only use cash, turn location services off on your mobile, and that way, advertisers won't be able to target you. I'm not bloody pregnant! Julian Morrow to the returns counter.
Do you know what?
All right, hopefully that had a few new angles to it. Well, people know about the retail transaction analysis, the target example, for a while. When we go to association rule and co-location, we'll actually come back and revisit it. But what you are seeing now is, the location traces. You saw the vehicle traces and your smartphone traces, and even those are now really getting heavily used, right? And that is sort of the topic of today. So we are intersecting data mining with spatial data, right? And it's here, it's not in the future, right? There are tons of spatial data, and people want to find patterns. And they can use classical techniques, that's one way to do that. But sometimes it's better to use custom techniques, and this talk will focus a lot on custom techniques. Okay? So before we start the topic, any questions, issues on this general topic and why we are studying it and so on?
So the concept of data lakes which is coming in,
Yes.
that is an extension of this one. Or that is
Okay, so that's a very good question. In fact, alright, so I will try to pull out one other article. Okay, so there is this whole broad area of, nowadays it's called business analytics. Okay, the names have changed. In 60s they would call it decision support system. Okay, so different names have come. Then became executive information system. Now they call it business intelligence, and even these terms like big data and all are sort of these umbrella terms. So in that space, you have a sequence of technologies. Okay, one core technology there is database management. And remember, day two we were kind of in that space. Okay, nowadays relational database is the dominant technology to manage your data, and it has some extensions for spatial. We talked about it. Okay, but from there the next set is often we would call it data warehouses. There is a lot of vocabulary in that term. And the main difference between relational database and data warehouse is your logical data model. Okay, and they are basically saying, people who are interested in just understanding patterns, they don't want to be writing the relational join and project and select, right? But instead they want a summary view. So remember some statistics we were doing, min, max, and so on. They just want to just look at these summaries. So in data warehouses, you create whole bunch of summary report beforehand, and you allow people to navigate the hierarchy of summary report, drill down, roll up. So there is a slightly different set of operations and interfaces. In 1990s, these two worlds were separate, okay, and they used to debate each other. But by end of 90s, more or less, the database companies bought out the data warehouse companies, and now today they're all the same, under same umbrella. Okay. Now the data lake term comes from data warehousing. Okay. Another issue in data warehousing is to actually pull together all the relevant data in one place. So people don't have to go around, trying to say, where do I get data from? Whereas in relational databases, the focus has been on management of data within a single organization. Okay. But as you know, if you want to analyze any, interesting phenomena, you need a lot of external data as well. Like, many things in the video, when they were analyzing consumer behavior, you may be even a big retail store like Walmart or Target, and you may have a lot of data on your customers, but it is still not enough. You need to bring back demographic data from census. Okay, you may want to go to Nielsen, which is sort of the rating agency. So data warehouse, the idea is that you want to make it much, very, very painless for executives and others to quickly come and get a summary report. So they bring all these data sources together, right, and pull them together in a consistent format. Not only that, they even anticipate the questions these executives want to ask, create all the summary reports, everything is all done, and they can, executives can come and quickly just walk around the summary. So the notion of data lake comes from data warehouse space. Okay, they have many other names there. Then they may call it data mart, okay, data warehouse, right? All of this is from that space. The next, so this is 90s. This was the front, cutting edge. All right. From there, it evolved to data mining, which is what we are talking about today, right? So here we assume all the relevant piece of data has been pulled together, formats have been sorted out, and you also have nice indexes and pre-computation, so I can do things fast. But what has happened now is we want to move the analysis one step up. It's not just summary report, it's not just group by aggregations, but we want to dabble in statistics, right? Why do we want to dabble in statistics? And I will come to that in a minute. But in database world, we have an assumption. It's called closed world assumption. How many of us know what that is? If you are in SQL, what is a closed world assumption?
The data which is there in the database,
Right.
that can only be queried.
Exactly.
we
So
can't-
what is an example of a question that SQL is not good for?
If you want to predict something.
Perfect. Perfect. So if you want to do prediction, what will happen tomorrow? What's the weather tomorrow? And you go to SQL system, it basically will say, I don't know. I know what happened yesterday, but I don't know what's going to happen tomorrow, right? And those are important questions. And if you want to do that, then you have to be in the space of statistics and data mining, right? The prediction model. So that's where sort of we are going today. So we are going to look at the data and extrapolate, okay? So this is sort of the next piece of that puzzle. But this whole spectrum is broadly called business intelligence. And if you're interested in that big picture, there was a very nice review article in Communications of the ACM a few years ago. And I said in the break, I will pull that out. It's by Surajit Chaudhary, who is in Microsoft Research. If you want, you can just go and search for Communications of the ACM Business Intelligence Overview, but I will bring that up. Okay? Same way, when you talk about big data, that's another sort of piece of this space where they have gone back and talked a lot about the hardware and so on. How do you scale it up? Okay. Does that help what we are doing? Okay. So spatial data analytics, same way, this course was this big broad umbrella, and we are touching upon a few pieces. We touched upon database, right? We touched upon data mining today. And then I said, we are picking other topics like network analysis and so on, which are relevant to this space. Okay. Yeah. Any other questions, thoughts on how these pieces fit? Okay. Yeah, terms come, then data analytics then became big data, which is another umbrella term. And now the next name is data science. How many of us heard of data science? Okay, that's the new term. And the meaning is still getting defined, So right now, anything you hear about data science is, one opinion. It's like elephant, right? 7 blind people figuring it out. But in few years, maybe that's the umbrella under which things will be consolidated. Okay? All right. So let's take a look at spatial data mining. And I'm going to start quickly with motivation and show you the pattern families of interest in this space. The second topic we actually don't have to do much because the second day when we were talking about OGIS data types and so on, that's what it is. It's just a quick review. And then we'll go down to statistical discussion and saying what do we need to know from a statistics perspective in order to interpret the rest of this properly. Okay. And then finally, this is the heart of the discussion. Chapter 4, 5, 6, 7. These are the pattern families which are most common or popular in spatial world, and we'll essentially go down each one, one at a time, try to first show you, if you know classical statistics or data mining, how you would think about it, and make an argument saying why you want to go a little bit further, okay, that It's not enough to know classical data mining or classical statistics. You want to learn some new ideas, okay? And then try to wrap up, okay? All right, so let's quickly go into motivation. And the idea is to show you some use cases of the spatial data, which will hopefully be, a little bit distinct from what you might have seen in other spaces. Okay? So this is, as I told you, the holy grail where all this is coming from is decision making. Okay, you can go all the way back to 60s and so on. And the idea is, if you go to many organizations, decisions often are made by gut feeling, right? This person says, I got all the experience, I know what's going on, and this is what I think is the right thing, and they are the experts. And even today, vast majority of discussion, or the decisions are made that way. Okay, they are done it on golf course or over a dinner, over a drink, and it's the person's experience and thinking and so on. And so that does go on, but more and more we are arguing that the decisions should be informed by the data. Okay, they should not be dictated or controlled by the data, but they should be informed by the data. Okay, so this whole thing, that's our bias. We want to say, well, look, lots of data is becoming available, whether it's through database or through sensors. There are a lot of examples that you saw. In case of the target example, those are your business transaction. We have been talking about GPS tracks, satellite imagery, and whatnot. So that's sort of your bias. Now, in past, the amount of data was somewhat reasonable, and people could analyze this by hand. So that's the statistical tradition. You actually hire a whole bunch of data analysts, which is still done. If you go to government agencies and so on, you will have number of people who are called data analysts, and their job is to actually collect the data, summarize the report, create an analysis, and then give it to the executive. Okay? High level executive, for example, President of United States, every morning there is a thick report, 30-40 page, which is a summary of everything the 12 intelligence agencies have gathered and analyzed, and say, okay, for the president who has to deal with the international or domestic issues, these are the pieces of information they should be looking at. And you probably heard our new president-elect doesn't want to read that report. So they are figuring out how to convey the information. Maybe the vice president will read the report and tell him. But this is very common. Most CEOs and so on, they all kind of every morning, 4 a.m., they sit, get up, they want to get the company's big picture, okay, and they make decisions based on that. But the catch is the old paradigm where you have a bunch of humans writing these reports is no longer viable because the volume of data has grown a lot. It's just going to overwhelm the number of people you can hire to look at that. But that doesn't prevent people from hiring them. Even for satellite imagery, as I was telling you, Brazil is very concerned about rainforest. So they have roughly 300 people, and their job is daily essentially go look at satellite imagery of entire rainforest in Brazil and stare at it and see, did we have logging somewhere which was unauthorized? Okay, 300 people watching Brazil. You can imagine how many people are watching rest of the world for conflict and hotspot. Okay, when South China Sea the conflict goes on, there are people sitting there watching these satellite imagery saying what happened there on the island, did they put a new structure or a ship and so on. Thousands of people, that is their job. But you can't really, it's not sustainable. They can't all be watching tweets and they can't all be watching GPS tracks, So you need some algorithms. You need some things to try to make life easy and prioritize things, okay? So in this space, there are a lot of tools. We saw, this is the tool from 60s and 70s where we said, okay, SQL can help you summarize and get subsets and some relevant things. The tools keep moving up. It became data warehouse, and then it became data mining, and now you're talking about big data and data science. The names will change, the techniques will get richer, but at the end of the day, you need some kinds of algorithms and computerization to prioritize the information, summarize the information, so on. Okay, so we are under that umbrella. And this is sort of quickly tell you why what we have studied so far is not enough. Okay, and we already went through that, so we'll quickly ask this. So if you are in the database paradigm, there is a closed world assumption. Okay, we can't talk about tomorrow. We can only talk about yesterday or this morning or last hour. So you can't predict things, and this is a space that you are going to need statistics and so on. In addition to that, I also told you a few other things, that SQL world is limited by transitive closure, right? They couldn't even do transitive closure in relational databases. But yesterday I did show you that they did add a few statements. So now you can perform transitive closure, but the performance is not great. But there are a lot of questions which are even more complex than transitive closure. Okay, transitive closure is an n cube kind of operation, but there are many questions, which are pertinent in data mining, like association rules, where the complexity is. How many of us have taken association rule and can tell me computational complexity? Okay, what is its asymptotic worst case computational complexity? 2 raised to n. It's one of these NP hard kind of situation, right? Clearly SQL is no match for that. Okay, anything more than n log n or n square, you don't want to be looking at SQL. Okay, so you need new tools, like same thing, clustering, segmentation, all of these problems are much more expensive than what you can think about in SQL. Okay, so that's why you have a new family of tools. Starting late 90s, this became very big and broad, but there were pioneers who were even trying this earlier in 80s and so on. Okay, so here are some of the examples that you probably have seen in your statistics or data mining courses, and that's the space we are in today. Okay. All right, so let's quickly define what we mean by data mining. Okay, the basic definition of data mining centers around a couple of keywords. So one keyword is this pattern. All right, and so whole data mining enterprise is concerned about finding patterns. And you may ask me what is a pattern and what's not a pattern, and there isn't a very formal definition. I mean, at most they can say whatever is not random is a pattern. Okay, but this notion we will informally with examples try to help you get a handle on. Okay, and then there are 3 adjectives that they talk about. This is the one adjective will tells you that this is an applied research field. This is not basic research. In data mining, we are always interested in a particular use case or a particular set of users and what they really need to be done. Okay, so this is an applied field, unlike statistics, which was more theoretical field. Interesting, which means if the pattern is well known, it's usually not interesting. If I analyze all the spatial data about weather and I come back and tell you is look, Gurgaon has same weather as Noida, you probably know that, right? It's not interesting. So, but you want to find something new, novel, which is possibly surprising, and that so that's another part. And then finally, the space of candidate patterns is very large. So you cannot just hire people and have them shift through that by hand. You need computer algorithms. Okay. Now, in case of spatial, the only thing I'm adding to these is that our data set is spatial. Okay, some of the data has location, and that's why I call it spatial data mining. That's about it. So next, what I'm going to show you are a bunch of popular pattern family examples to help you understand the space what we are talking about. And these pattern families I'm going to take from spatial world. One of you, we saw a little bit. So the most, I would say, popular pattern family for spatial data is hotspots. Okay, and I'll show you some examples. Some of you might remember we saw that before in day 1 as well. Another pattern family, which is the opposite of this, is anomaly, and actually more precisely spatial anomaly. Okay, and I will compare and contrast it with classical outliers. The third ones are these interactions. So you heard about that target, a couple of examples of that. In classical data mining, we call them association. In statistics, we call them correlation. And here we are using a slightly different name, co-location, co-occurrence, and you will pretty soon know why the names have been changed. They are, similar but a little different. Okay? And then, of course, prediction models. Again, I have put an adjective to remind you that they are a little bit different than what you know from regression and so on. Okay? So let's go look at the examples of these. So we'll start with hotspot, and many of you remember this map, right? If day 1 we were talking about it. So in this case, Gian Jnu saw that the cholera deaths were localized in space. They were not all over London, right? There was a small area. And of course, he did it intuitively, right? He did not have statistical tools, but today this data set, you can feed it through SAT-scan, and it will also give you a statistical measure of saying, what are the chances this happened by, just because of randomness, right? But this is the idea of hotspot. And this pattern, as I said, had a lot of impact on our civilization. The science, the germ theory was born because the hypothesis was changed due to this, right? Today, this pattern is again used a lot in public health. If you are looking at environmental, or infectious disease, they often would, put data on a map, they will run through this analysis. If they find certain hotspots, they would analyze it further and say, why is the hotspot there? Is it because in that area people are much older? Is it because they have a lot of smoking? So they can first take out all the known factors. And if the pattern still persists, maybe it is environmental cause. Then you have to go and look at, is the water polluted, is the air polluted, is there a mine which is sort of giving you some exposure and so on. All right. By the way, so this pattern now has also moved from public health to public safety. Many police departments are now running this, and if they see crime hotspots, they try to think about different interventions. It could be sending more police for patrolling there, or it could be social intervention. Try to go and understand what's going on. Is it because there is not enough employment? Is it because of other factors? But this pattern is widely used. Okay. Now it's also is getting a little bit of evolution, and you saw that before, because the data sets have gotten richer, and I'm going to show you a few. So if you are in urban areas, then oftentimes the phenomena is constrained by the transportation network. So instead of finding this circular or ellipsoidal pattern from SAT scan or k-means, you should also consider looking at another summary which are linear, right? And same way, nowadays your data comes with not just location but also time. Okay, so this is Amsterdam crime report over 24 hours, and oftentimes two things happen. First, your hot spots are not static, they grow and shrink and then they move, right? So there is more richness of complexity, but you can also have other interesting patterns here, right? And that's where I will leave it for now. Okay, let's look at the second pattern family, which is sort of the opposite of hotspot. Okay, hotspots were sort of like clusters, groups, just that they were localized in space. And these are sort of the observations which are not part of any groups. They just are by themselves and they look strange. So let's again go through the example. So suppose I am showing you traffic data in Twin Cities. And so here is actually the sensor network. As you can guess, these are the highways or freeways in Twin Cities. And roughly every mile they have loop detectors. So in the pavement there is a big piece of wire which is a pressure sensor. So when the cars go over that, the pressure changes, and based on that there are models to estimate speed, traffic density, volume, and so on. Okay, so there are roughly 4,000 sensors in that area. And 1984, this was one of the first sensor networks in US. Seattle and Minneapolis started it, and it proved so useful that about 1990-91, 40 other cities replicated it, and since then many cities around the world have done that. I'm not 100% sure with Delhi, whether Delhi has it, but I would guess near flyovers and so on, they probably have these kind of sensors. These are also augmented by a bunch of cameras, so there are a few hundred cameras as well on this. But let's look at loop detector data, and this is showing you behavior on one highway on one day. So we have picked up this I-35W, which is one of the major interstate, going through, this is sort of Minneapolis downtown, this is St. Paul, and we stretched it out from north to south. It's the 60 sensors, about 60 miles stretched out here. Okay, and this is time of the day. This is sort of midnight, you can guess, morning, afternoon, and the color code is traffic volume. Red is high and blue is low. Okay, so looking at this data, you can see many patterns already, but I will focus on one to illustrate outline. So first, you can see morning rush hour. Okay, so people from this side, they are going to work in downtown. Okay, so this is space. So people are coming from residential areas, suburb to downtown to work. Okay, and evening they are going back home. But you can wonder, why are they not going back over on this side? Why are they going the other way? Because this is showing you only one side of the road, southbound. Okay, so it's going from here to there. So people who came from this place to work, they went back in evening, but they were on the northbound. Okay, so if I showed you the northbound, there would be a mirror image of this. Okay, so people who were going back home in the evening were actually living on the other side. Okay, so that's what you're showing. You can see some other things as well. It's always good to look at your data. This is a mistake a lot of people make in data science, that they just take the data and they run the algorithm and they're happy. So when you look at this data, you also start to see missing data, right here, right? And that happens. A lot of sensor networks, you have different kind of failures and so on. But a more interesting missing data is this line. You see 2:35 p.m. There is a blue line. Data is missing for every single sensor. Any guess what happened there?
Power cut.
It's possible, but it's unlikely scenario. U.S. power grids are very, very robust. Any other guess? But there is no traffic on entire system. And that's middle of the day. Remember, this is actually roughly middle of the day, till noon time. What? Okay.
Something which block the sensors like weather change and sensors.
It's possible. These are hardwired sensors. Okay, so these are complete wire, very heavy protection. These, because of Minneapolis winter, these are in an enclosure which are heated, and you have actually windshield wiper fluid and everything. These are very, very robust sensor systems. Not like the sensor network you talk about in computer science. Yeah. Any other guess? Okay, so it's closer to that. So in back in '84, these files will grow a lot. So every day they would switch the file. That was their procedure. And it just turned out that when they were switching the file, they missed one particular 5-minute interval. So these are 5-minute granularity. So it had to do with the procedure of data collection. But anyway, one should look at the data. That's all the message is. So you can think of this also as a discontinuity in time. But the one we want is discontinuity in space. And you see that happening at sensor number 9. You see that line? There's something strange about this sensor. So let's look at first, what's going on. So this sensor, if you look at individual reading, that's the color code. Individual readings are not globally anomalous because I do have a lot of that color all over the place, right? So if I only am looking at sensor reading, you cannot argue that individual readings of this sensor was way off the norm, okay? But if I am looking at it spatially, there is something strange about it. What is strange about sensor number 9? Look at the sensor upstream and downstream. They register no traffic. Midnight, right? This sensor is still registering traffic. It's very different than its neighbors.
Some turning road or something like that.
But these freeways, has no signals, no turns, it's very restricted. It's sort of like your flyovers. You can enter and exit, but these are not road intersections, okay? So the cause is something you have to involve domain expert. But we can at least say, look, there is a discontinuity in space. And you remember space, I said there is autocorrelation, there is smooth variation. So anytime there is an exception, discontinuity, it's of interest, that's all. We don't know why, but we can say, look, there was something strange about it, okay? So you can write algorithms and you can find out this sensor is very different than its neighbors. And in this case, when we showed it to the DOT folks, they basically thought it's a bad sensor. So as you said, time to time things do go wrong, but it will be like one sensor went bad, so they have to dig it up and put a new sensor, okay? But that's the idea of spatial anomaly, and that's different than global anomaly, right? Everyone sees what the example is, okay? So discontinuities in space, okay, well, maybe I will leave it for the tutorial, but most phenomena in space are smoothly varying, and if you see a discontinuity, even in calculus, remember we talked about discontinuity, those are often interesting. Okay, let's go to the third pattern family, which is the prediction model. And at least on the surface, this will look somewhat like prediction in other spaces. So here is a data set for a marshland. These green areas are where you have vegetation. And then, these red crosses that you see, this is where you have nests of a particular bird. Okay. And for many cases, like in environmental sciences and so on, people want to predict where certain kind of species live. If they are endangered species, during development, you try to protect that area, right? And so this is the use case here, and this was actually a real thesis. This data was collected by a student in ecology, and people in computer science, you can appreciate their contribution by knowing how the data was collected. So this gentleman actually had to put on rubber boots and go in this wetland, and he walked this, basically feet by feet, and he made, so there are 5,000 of these green pixels, each is 5 meter by 5 meter. So they manually went and surveyed the whole area to record this data, okay? And, and other maps also. So here is another attribute called vegetation index. This is dense vegetation, this is, water, and that's sparse. Many of the other explanatory variables. This is sort of distance from water, depth of water. And a lot of the field work, people do that. So, as computer scientists, we should be very appreciative that they actually collect the data, create the ground truth, and then we can play with them and do the modeling. But here the question is, if I gave you these kind of explanatory variable like distance to water or vegetation durability, could you make a model to predict the locations where this bird would like to nest? Okay, that's the basic idea. And on the surface of it, it will look like what other prediction like regression and so on. Okay, but when we come to the detailed discussion, I will argue that you need to go a little bit further than that. Okay, all right. So everyone comfortable with what the prediction is? Okay. So you have to build a model, and if I gave you a new area with these variables, then it will come back and say these are nest-worthy areas. Okay, good. Let's so again, for example, risk map predictions are of the same family. All right, the fourth one, I think you saw that on day one, but I will just remind you that we also are interested in correlations in space. Okay, and some of you remember this map we looked at, where you have maps of many different things like bluebird and house and so on, and you want to essentially say are there pairs or triples which occur together in space. Again, this has a partial predictive capability. So if I see one, I can predict that the other one is in the neighborhood. Okay, it's not a complete prediction model, but it's like correlation partial prediction modeling. And in this picture, you probably remember we found some of these pairs, like this house and bluebird, tri-tree and fire, and so on. Okay. All right. So these are some examples of patterns in space. But before going further, I want to do one other thing, which is good for academic discussion at least, to say what is not spatial data mining, so that we can scope our discussion. Because at least in popular media, the meaning of word data mining got stretched a lot. Okay. So even if you are doing Google search, they would call it data mining. Okay. Actually nowadays, same way, machine learning word is stretched so much. You want to do Google shortest path, New York Times calls it machine learning. But in academic literature, we don't want to call it machine learning. Okay. So at least here are the things I'm not talking about. So I don't include SQL query. Okay. So what we did on day 2 in our discussion, it's not data mining, it's database. Okay. Same way, if you are coming from statistics, and then finally, I'm basically going to stay away from non-spatial data. Okay. But of course, it's a philosophical thing to say that really what are non-spatial, because we live in physical spaces, so everything does have a location, but oftentimes people ignore it. So if you don't have location data, we are not really interested. Okay. So even how many of us know this pattern, diaper beer story? Some of us. Okay. Surface of it looks like non-spatial, right? But if you know the whole story, do you know is this pattern true everywhere in the world? Probably not, right? I mean, there are parts of India where they don't really consume alcohol, and they don't use diaper. So there is a spatial footprint, right? Even in the US. So the whole story is that it was true only in blue-collar neighborhood and only in the workday evening. Okay. Of course, for simplicity, they left that out. Okay. So philosophically, almost all data that you deal with has a location, just that many times it's not collected. Okay. Okay. This is a quick question, so why don't we think about it 30 seconds? I'll take a quick question.
So why isn't hypothesis considered to be a part of, because you need to have some hypothesis to
Right.
have a little bit of predictions.
Okay. Very good question. So again, I will give you the big picture first. Okay. So there are 3 at least disciplines which are very overlapping. One is statistics, which has been there for almost 400 years. Then came along machine learning, which has been there at least since maybe 60s, 70s, but 80s certainly, right? And they were taking some statistical model and trying to speed it up by watering down statistics. And the new kid on the block was data mining, which happened in 90s, right? So the first question was, why do you have data mining? How is it different from statistics or machine learning, right? So that's where this, one of the distinction that was made is the following. It said was data mining was about hypothesis generation, not hypothesis testing. Because hypothesis testing was already well explored in statistics, and it has a lot of value. I'm not dismissing it. But all I'm saying is that we are not trying to do that. Somebody else does that. Okay. The value of data mining is in hypothesis generation. For example, go back to London cholera. You know what was the prevalent hypothesis, how cholera was spread at that time? No, that happened after this. Okay, water hypothesis was generated out of Gian Jnu's map. But before that, what was the prevalent hypothesis of air? Maizama bad air theory. So you can go and test that hypothesis. What is it going to do? Every time you will say, okay, reject, reject, reject. And they did that for 100 years. That's not the value of data mining. You say, well, what are the hypotheses that's shown by your data? Right? Does that make sense? Yeah. So it's a different value proposition. And these are complementary. Once you generate the hypothesis, you cannot just stop there. Right? You can, at least in physical domains. In social science, it's harder to test hypotheses. You can't do control experiments with humans a lot, right? But in physical sciences, you can do control experiment for many small phenomena, right? So if you can engage in a hypothesis testing with a control experiment, you should. But that's out next. It follows the data. Really, there are a lot of ethical issues. Can you really subject a population with that controlled experiment where you know that maybe you're doing the wrong thing, right? So there are many spaces you can't even do that, and your whole knowledge is based on hypothesis generation to see which. So what you do is, beyond hypothesis generation, the other thing you can do is hypothesis ranking, right? So you can say, look, based on all our domain knowledge and thinking and meditation and whatever, these are the hypotheses we think are interesting. Then based on data, I can generate more and then rank the hypothesis and say, okay, this is the hypothesis which best fits the data today. And maybe a few years later with new data, I might have more hypotheses, right? So that's how the knowledge proceeds. Okay. Good. Any other thoughts, questions on this? Okay, particularly when you apply data mining to physical sciences, you have to know the life cycle of knowledge generation. And if you stop at hypothesis generation, you will get a lot of flack from physicists or biologists and so on. But if you're working with social scientists, you probably won't. They would be happy because that's all the nature of their subject is. Okay?
Testing is not a part of data mining.
It is not. If you want to do hypothesis testing, talk to a statistician. Okay, they know how to design experiments well and how to test hypothesis well. Okay. Right? Any other questions, thoughts, and so on? Yeah.
Can you please say something about footprint?
Okay, we'll come there as we go through the pattern mining. So right now we'll go through these 4 patterns quite a bit. The closest to footprint you saw here were hotspots, because hotspots gives you a little piece of area, right? So it is a footprint of some phenomena. Okay?
How is it different? Because in ecology, footprint means something else.
Oh, what does it mean?
Ecology, it means whatever I have studied, I found out that in ecology, the factors which are essential for the sustainability.
Oh, I see.
Footprint analysis in ecology, we study about factors that are responsible for the sustainability of the land.
I see. So if you're looking at factors, they would be, I think, closer to correlates, right? So those would be closer to the collocation, association, correlation family. And that's a good one. Actually, I haven't used the word footprint here, but I think you're referring to the change footprint analysis. Yeah. Okay. So maybe, as we go along, we can maybe come back or one-to-one talk more about it. Yeah. Any other thoughts, questions on the motivation? So far all we did was to try to motivate you, say why this topic is interesting. Okay. For each pattern family, I will get into the details of what methods are there. Okay. All right. So let's quickly look at that. Okay. A. So I want to ask which countries are very different from their neighbors. Example like Israel, right? Very different from everybody around it. Okay. Spatial outliers, right? Everybody sees that? Okay, good. Which highway stretches have very high accident rates? Hotspots, pretty linear, right? So for a hurricane is coming and I want to know where will it make the landfall? Location prediction, okay. Of course, here there is a lot of physics that goes on, so you need to go beyond just data crunching. Okay. Which retail stores often tend to be together in a shopping mall? Location, right? And what's the distance between 2 cities? It's a querying, it's not data mining, right? Okay, good. All right, so let's carry on. As I said, the second section I'm going to skip. All of you remember OGIS data types, and that's what it does. So I will click through it, but I don't want to spend time on this one. So as I said, in geography, location, it matters, and you have different type of data. We spent actually a lot of time on OGS data types, which is the example of vector data, points, lines, polygon. But in geography, you also have these gridded data like satellite imagery. They are very similar to the imagery you take from your camera, just that they are geo-registered, right? Even your camera images nowadays are. And then road maps are usually graphs, right? So these are three genres. And then, we have also relationships. From data mining perspective, one thing you have to remember is the following. In the traditional data, when you are in relational database in ER diagram, all the relationships are in your schema. And because of that, they are also in your tables. So relationships are explicit, okay? But in spatial data, the relationships are often implicit. We don't pre-compute and store them, okay? So if you are mining spatial data and using even the old techniques, even if you want to do regression, the least amount of attention you want to pay is feature selection, okay? So distance to road or distance to water, those things you may want to pre-compute as a feature and feed it to your regression or whatever else you are using, okay? So this is a big simple pre-processing step that is required. And it's a common mistake also, I will tell you that. For example, neighborhood relationship, okay, which pixel is next to which pixel is very important, okay? But if you go to UC Irvine machine learning repository, how many of us know about that? We have used it, right? Machine learning community loves that. It saves them time to collect data and understand data. There are spatial data sets there, and W matrix is missing, okay? So they have destroyed the space completely. So whenever you take this data off the web, don't use it blindly. Try to think about what they have done, okay? All right, so as I some of these things, if you understand that, and so besides the OGS, which is for vector data, for raster there are other kinds of operations, and that's all I would basically say. OGC we did cover, and you probably remember all of these operations that we were talking about. If you don't want to remember any detail for data mining, at least remember distance, okay? That's the least you should do. All right, we have nice mathematics of this, you remember those, we talked about it. This is a little more math notation, the original paper, but basically, we know the 9 intersection model. And also we should know that OGS model is not the end of spatial, right? There are a lot of things it does not do. For example, it doesn't capture the direction predicate, does not capture 3D kind of things, does not capture roadmap, certainly limitation on space time, and so on. As time goes by, you will get even richer models. But today, at least start with OGS, okay? That is a good thing. This probably we should know very quickly. Okay, how many vote for A? A lot of us, good. This is the traditional, the classical relationship, these three are spatial, okay. All right, let's now get into a little bit of statistics. Yeah, go ahead.
Question on this.
Yeah.
Now, when we do classical data mining, we have a choice in picking up of distances.
Okay.
Now, whereas in spatial, Euclidean, I think fits in the best.
No, I would not say it is the best. You have to understand again your domain, all right? Euclidean, as you know, makes sense if you are flying, okay? If you want to fly a airplane, a helicopter, or a bird, Euclidean is okay, at least in small distance. Large distance you want spherical or whatever, but that's a geometric distance. But if you are in an urban area, you are highly restricted. Then what kind of distance would you prefer? If you are driving a car,
That is dictated by the routes.
that's dictated by the network, so that's a network distance, okay? And I will show you in other cases, it may not, the neighborhood relationship may be more interesting, right? So in physics, how many of us know diffusion pattern? Some of us know like temperature, mass, right? So if you think about infectious disease, which is being carried by water or air, it's a physical diffusion process, right? So in that case, that it kind of goes to the neighboring location over time, right? So the neighborhood is kind of interesting, but distance may be a proxy for that, okay? But then you have to see what are the channels for airflow and water flow and go along that, okay? But since you are coming from GIS, I don't want to give you that simple story, do the distance. That message was for the computer science data miners who don't want to engage in space a lot, okay? So a lot of messages I am giving out are for different audiences, okay? So the message, if you are in machine learning and you love your machine learning and you want to do your SVM and deep learning, I am not dissuading you from doing that. but at least feed some spatial relationship as a feature to your deep learning. That's all I'm telling you, okay? But if you are coming from GIS, you know a lot about space, and you should be using a lot more features and a lot of these models, okay? That's all.
So we should possibly, as in urban case, go for more of network distances, and whereas open spaces, we can look
Right.
at the Euclidean oblique curve.
Right. So again, you are from GIS, so I will take it one step further. But even in urban spaces, look at the phenomena.
Sir,
If you are looking at infectious diseases,
then it is aerial,
then it's going through air or water and take those distances.
absolutely.
But if you are looking at a human moving on the road, right, not helicopter,
Understood.
you look at different thing. Like, pedestrian fatalities is a different thing, right?
Understood.
But you are looking at aircraft accident, it's a different thing, right? Yeah. All right. Any other good, things? And for computer scientists also, I will tell you, if all this detail bore you, you don't have to learn and do it yourself. Find a partner, okay? Find a partner who is geographically aware and work together. And that's the best way to move forward. Computer science as a discipline is used in so many domains. We can't expect a computer scientist to go and learn all those domains, okay? Just not feasible. But at least we can find partners in that domain. So we work together and make it sensible to both, okay? And that's how we have always done it, okay? Any other questions, issues? And that's another reason I will remind you, just like day 2, today in coffee hour, try to meet a new person, preferably from a different discipline, okay? All right, so let's go touch upon statistics just a little bit. And even though data mining is different than statistics, but it behooves us to understand a little bit of statistics, okay? Because if you are, statistics is much older, right? 400 years old. And in many domains, they have actually made a huge impact. So those domains respect them a lot, okay? If you are in medical domain and you are looking at, evaluating a new medicine, there is a long statistical tradition to do controlled experiments. And if you are not aware of that, you go and show your patterns, you might lose face and credibility, okay? Precision agriculture, there is a long tradition of testing seeds using statistical experiment design. If you just show up with your association rule, you are quite likely to lose face, okay? So be aware that many domain statistics is highly respected. And that's why when you do your data mining, if you're talking to that domain, at least try to translate and make interpretation. And that's why I want to touch upon just a little bit of statistics. But of course, there are other domains, like social science, where statistic traditions are not as much, and you might have a better time going forward. So I want to touch upon just a little bit, and we saw some of this on day 1. But in, specifically, I also want to tell you that there are 2 types of statistics you should be aware of, okay? So let's go and look at the classical one. And I alluded to that on day 1. So classical statistics started, well before computers were invented, and they often did things to simplify calculations, right? And one of those things was this assumption, calling the data samples are drawn independently of each other. Because with this assumption, you can hand calculate, like regression model. How many of us did actually a hand estimation of a regression model in your school? So if I gave you a set of points, some of us did that, right? And in one scan, you can calculate all the coefficient. It's because of this assumption, okay? So as I said, it simplifies hand calculation, and that's okay. But in space, this assumption is troublesome, okay? Remember, we talked about it. So people actually want to model this autocorrelation, and now the computers are powerful enough that you can actually start using these models, okay? And there are, we are actually now going to show you some measures of autocorrelation. So you don't have to take my word for it, but you can actually compute metrics, and they would tell you, like, in particular, Moranza is normalized. So if your data set, this value is 0, then you can say, yeah, this assumption is okay. I can go back to old statistics, okay? But it will also tell you that no, it's highly autocorrelated. Look at new models. I will also mention in a few other measures. So just like Pearson correlation coefficient, I will talk about spatial, and then it takes you a little beyond autocorrelation to other issues like heterogeneity and maybe even edge effect. Okay. So again, a quick glimpse of that space, and again, show of hand, how many of us taken a course on spatial statistics here? At least one. Okay, good. Which department was the course offered, and which institution? Oh, good. And you do have a course on spatial statistics or geostatistics?
In fact, I'm working on identifying urban growth potential sources.
Okay.
So, I'm
Mod.
with multi-criteria evaluation.
Wonderful, wonderful, wonderful. And then you picked up statistics part on your own, or is there a course? Because if there is a course, it may be of interest to a lot of people.
No, I haven't done any course.
Okay.
Just,
From the project, Okay, good, good.
We have a course when you start, before you start JS.
Okay, good. And this is which institution and department?
And I think again, computer science department.
Oh, within computer science. Wonderful. Who teaches that course?
Dr. Devujyoti.
Oh, okay, that he has been writing a lot of emails. Okay, good. So, this is another thing to know. Maybe the course is not in your institution, right? But it may be in a neighboring institution. And if you are interested, partner and do that. For example, University of Minnesota, this course is not in Department of Statistics. It's in public health, So it could be in regional economics. It could be in mining. But if it is interesting to you, find those. So this is a good thing to know. NIIT actually has a course. And, you may have others in public health and so on. But this space, there are theories, and I'm just naming them. I'm not going to teach you the theory. But the first theory is applicable if your data is a set of points, like locations of disease or accident or trees. And we'll show you some ideas from this. So one of the idea here is this notion called complete spatial randomness. This is sort of the equivalent of randomness in classical statistics, and I will show you pictorially. And then you can essentially test if your data, so this is a test to see whether your data is random in space or it is not random, and I will see that. Okay? This is a second theory, geostatistics, which is often used in mining and so on. And this assumes that things are very, very heterogeneous. So you essentially do a local smoothing. And this is used to, for example, estimate rainfall, snowfall, and so on. Some techniques here are things like variogram. Kriging is a very well-known pattern. Has anyone used Kriging or variogram here? Some of us, great. Very widely used, came from mining to know where to dig. And then there is a third one. It turns out that a lot of spatial data, there is a concern about confidentiality. For example, health data. So many countries, there are laws. They will not give you individual information, but they will give you aggregate information that in this district, there are so many people who are ill. Census data, same kind of thing. So there are specific techniques to analyze these polygon aggregated data, and we will again pick up a few of those, and show you that. Okay. All right. So like leaving aside that, let's just pick up a few concepts. That's all we care about for now. The first concept is spatial autocorrelation, which you have heard before. And again, this picture I showed you before, and it gives you a map where the pixel properties is generated just randomly and independent of each other. And this map, as I was arguing, does not look like most maps we see. Most of the maps we see look like this. You have a lot of smooth areas, right, or regions, which means nearby pixels are similar. And and this is sort of quantitatively captured by autocorrelation in spatial statistics. And informally, it's captured by first law of geography, which said something of this kind. Okay. So we are going to touch upon a few numerical measures so that we can quantify this intuition. All right. So let's go look at some of these. The first measure is K function. It comes from point process theory. So you can use it if you have a set of points and so on. And what it does is very simple. It says, okay, let's pick a distance h. Okay. And if for that distance, I essentially draw a circle around each point. And I count how many other points fall within the circle. Okay. If these points were independent of each other, then this count will track area of the circle, right? But if your count is different, then we have something to do. So this curve, this is pi h square, right? This is the radius, and that's pi h square, the mean. You can also get a standard deviation band using Monte Carlo simulation. And then you basically look at your data set. Is this value of K function, is it within the band? If it is, then you are saying, okay, so you are very close to spatial random. So you can go back to classical statistics if you want. Okay. But if your values are outside the band, at least for some h, then you probably want to think about spatial methods. Okay. All right. So here are some visual examples. So let's try to guess so this is what is spatial randomness looks like. Okay, this is what spatial randomness looks like. If I try to compute K function on this, it will be somewhere in this band. Okay, somewhere in this band for whatever h value you take. Okay. This is sort of clustered data. So where do you think k value function would be? Will it be above or below? Above. Okay. So if you are out, above the band, it means these points like each other, they cluster in space. How about this one? It's below. These points don't like each other, right? It will be somewhere here. Okay. By the way, if you are looking at forest and trees in a forest, right, and it looks like this, what do you think that forest is about?
It could be a human plantation.
Most likely human planting, right? The natural forest probably looks either like this or like this if the trees are clustered. All right. So this is one quick measure. Now we can generalize this function to measure interaction between two sets of points. That's called cross K function. Okay, and its definition is very simple. But now what we are doing is to, let's say you put circle around the first type of event, then you count the second type of event within the circle. Okay, so suppose you remember that fire and dry tree example we are looking at. So you put circle around the fire and you're counting dry tree. Okay, or you can do the reverse, put circle around dry tree, count the fire. But other than that, it's very simple, and it can help you say whether pairs are co-located or not. And so remember this data set. So the cross K function for this actually looks like this. So this is pi h squared, and for some pairs, things are over here, but the two pairs, remember, we thought they were co-located way above the band. Okay, way above here. All right. So this is where the point process theory measures. There are many other measures as well. So if you are looking at polygonal data or satellite imagery, another measure is called Moran's eye, right? Gettys OR. There are a whole bunch of measures for different theories. And as you are interested, you can go pick it up. But let's look at the second idea, okay, which is heterogeneity, right? But any quick questions on K function or autocorrelation, cross correlation issue?
Cross correlation measure for raster data.
Is there a cross correlation measure for raster data? That's a very good question. So Moran's eye and so on usually look at single raster at a time. You can conceptually generalize it to two layers, but I have not seen that in literature.
Moran's eye is for autocorrelation.
Yes, indeed.
But for cross correlation,
It is. So you remember the definition of Moran's eye? What it is actually doing is to take a pixel and compare the value of neighboring pixel. So now I'm asking you to generalize it. Okay, if I have two raster, I take a pixel from first raster, right? But I compare the neighbors from the second raster. So you can try to do that, but in literature you're right. There are no direct, it's not in the literature.
There is a comparison of pixel between bands, which is
Right.
called
Right.
coefficient of variance as part of statistics. When
Right.
you study as to how much the band variance between one band to the
Right,
other.
right. But it's a local function. You take the
It is a local function.
right, yeah. So local functions, when you go back to local functions, they will look like traditional statistics because you have lost the neighbor relationship,
Quite close.
right? Yeah. And what he's asking is, can I bringing the neighbor relationship back to that, right? By the way, it also tells you the difference between Pearson correlation coefficient and Ripley's cross-K function. Pearson correlation coefficient does not care about neighbors, right? It's exact lining, same location, two attributes. And you can use those if you have nothing better. But this is a space for creativity, okay? Because most of you are doing research, and you should take this as an opportunity to define a cross correlation measure for raster data, right? And try it out. That's what research is about, right? And you may not have the perfect measure, but you would at least have a measure and you can evaluate its strength and weaknesses. Good? Yeah. Other thoughts, questions here? So you take your Pearson correlation coefficient, make it neighbor aware, and see how it works, Yeah. Good. Try it out with different situations and see when it works. Yeah. Okay. All right. So let's actually look at a couple of other issues that will come in handy as we talk about pattern families. So second law of geography, at least good according to Goodchild, it's not as well known, but it's about heterogeneity. And what it essentially, informally is saying, are two different things. There is a lot of non-stationarity, right? That's a word we know in time and so on, but also in space there is non-stationarity. The model you build for Delhi may not work in Bombay and vice versa and so on. Okay, and it has another meaning. If you take a heterogeneous population and you try to make a single model, that model may actually do a lot of harm. Okay, and some of you probably know this thing called Simpson's paradox. How many of us know the Simpson's paradox? Few of us. Okay, so I'll give you a simple example of this. Okay, suppose you go to a farm which has some cows and chicken, right? Let's say same number of cows and chicken, and you are asking what are the average number of legs an animal has on the farm. What will be the answer? 3. But there is not a single animal on the farm with 3 legs, right? It's a heterogeneous population. So you're better off separating cows and chickens and counting them separately. Okay, it's the same idea. So, but here what happens is, I'm showing you 2 variables. Okay, as you can tell, it's heterogeneous. If you fit a single model, looks like the relationship is positive, right? As this variable increases, that increases. But notice if you separate them out, in each group it's negative, right? So basically in heterogeneity, the least you should do is to try to separate out the population. And again, this issue is not unique to space. This occurs in lots of cases, okay? It occurs in non-spatial data, temporal data, all over. But all it is saying is pay attention to that, okay? But space, it's tricky. People should do that, particularly if your area is large, okay? The third issue is called edge effect, and I'm just going to illustrate it with via one example. So this is one of the earliest data sets we were given, going back to roughly 2003. Back then data mining was established, but spatial data mining was not. And the government agencies were trying to figure out, I have spatial data, I want to do data mining, there must be something interesting about it. So our group was actually first given a set of data sets by Army to say, okay, show me what your spatial data mining can do, and so on. So this data set was about North Korea, a whole bunch of layers, and we did different things. But this is one map where you are showing these green and red areas are croplands. Okay. You see the blue lines, these are streams, and the black lines are roads. Okay. Now some of the croplands have been flagged as red. Okay, and they are considered anomalous because they don't have access to transportation. Okay, so a cropland is green if it is reachable by river or road. Okay, if it is red, means it's not reachable. Okay, again, if you are familiar with agriculture, you know that crops have to be moved back and forth, right? So that's why you need transportation. But if you don't have transportation, okay, so what would be your interpretation? Why this might be interesting to public safety or public defense official?
If you don't, possibly it could be a location which has been selected or which is not to come up on the main this thing.
Right.
It could be a secretive location if there is no access to it.
Right. And what they may be growing there?
They could be growing anything just to cover it up. So like normally it has to be in harmony with the weather.
In Afghanistan, what will they be growing?
Opium.
Oh, right. So these are interesting to certain agencies. That's all. Okay. All right, so you can do anomaly analysis of different.
The nuclear sites would invariably have a crop which is slightly different from the...
Because of the radiation.
Because of the radiation.
Okay, so that will also be spatial anomaly.
Right.
Yes, or if you have buried ammunition,
Yes.
you will see a signature on top. Yeah. So there are a lot of use cases like that. Yeah. But what I want to illustrate here is the following. So we all know that there are some spatial anomalies here, right? How they are defined, don't worry about it. Okay. But my confidence in declaring this cropland to be anomaly is much higher over here. It's much lower over here. Why is that? Both of them are very far from transportation. But my confidence, and in space confidence is important because false positives are troublesome. I'm much more confident over here, much less here. Why? If you know what maps look like. Because I don't have the data on the other side, it's on the boundary. Okay, so you notice that in spatial data there is a notion of a center and there is a notion of an edge, and on the edge we lost data. Okay, by the way, this is true of all data sets, but just that in data science and machine learning you are in high dimension, very hard to understand what is the edge and the center, so you don't bother. Okay, but space, it's not hard to know what that is. Okay, so this is another thing, and as you develop your models, in statistical models there are quantitative methods to quantify, link your confidence to edge and center and so on, right? Okay, so these are different issues, and as I said, hopefully with NIIT course and otherwise, if you got interested, you can go there. But this point, we are just going to stop and say that spatial statistics again has done some things well. If your data is point data, you have very nice theories. If your data is sort of census type of data, you have some theories. But again, in linear data, the theories are weaker. Graph data theories are very, very, immature. If you want to do space and time, very, very immature. So this is again is a growing field, right? So don't treat it as a dead field or which was done 400 years ago. But the knowledge has to evolve, okay? And if you bring in new data sets and work with statisticians, some nice things will happen. So there are some nice theories like point process theory or lattice theory, and more things are needed. That's all. Good. So any quick questions on the basic statistics, and we'll do a quick review here. Okay, how many vote for A? Okay, B, C, D. All right, great. This is edge effect, right? Okay. All right, so now we are actually finally in the heart of the matter. We'll watch the time a little bit. So close to 11, but maybe we can do one topic before we break. Is that okay, or we want to take a break now? How are we feeling this coffee break timing?
Professor Punya had come and I think he left. So anyway, we can.
Okay, sure.
Oh, so
Sure.
that way we have time.
That way we have time. Okay, all right.
So
All right. So we'll do maybe one of these pattern families, and it's very close to spatial statistics, so natural place to do it together.
Yeah.
And about 10-12 minutes, then we'll break, okay, before we come to that. Okay. All right. So as I said, this is the heart of the matter, and let's start with location prediction model. And you saw a little bit of that on day one. Okay. So we are going to again look at some prediction models very quickly, which have spatial component. And you remember this problem. In this problem, we are basically trying to predict nest locations out of other maps. Okay. On the surface, this looks like any average prediction problem. In fact, if you were in statistics or machine learning, you will change the representation, right? In those areas, you make a table out of it. Okay. And we can think about what the table will look like. So how many columns would that table have? The people who do machine learning and statistics. 4. Okay. Location 1, 2, 3, 4. Right? This is the class column, and these are explanatory variable. How many rows will the table have? That depends on the pixel. This data set is about 5,000 rows. Okay. And once I give you the table, if you have done statistics machine learning, I can ask you what model you might use. Right? What will be the vote nowadays, which is the most fashionable prediction model? A little bit louder. Neural network is one. Which neural network? Okay. Any other beside neural network? Agent-based model. Okay. All right. We'll come back to agent-based model. It's slightly different family. It's better for your urban sprawl and so on. But this is much simpler problem. Yeah. Which other? Support vector machine, SVM, is very popular. No one came up with deep learning, but neural network and deep learning are pretty close. Okay. But by the way, by far the most popular. Well, this is pixels, so you can decide whether it's image or not. But basically, with another one. So within neural network, there are variations, and you can choose them. By the way, by far the most popular prediction model is regression. Okay. Then you can do other things, decision trees, but there are dozens of them, and you can do that. Okay. But most of them again suffer from IID assumption. Okay, unless you do convolution and the image one. So that's the main thing. It kind of says you need to go beyond it. So to go beyond that convolution, the independence assumption, you have to use this neighborhood matrix. So let me quickly define what it is. So here is a very simple data set with 4 polygons, A, B, C, D. And this is its adjacency matrix. That's one way to define neighborhood. So for example, B is a neighbor of A, C, and D. So B is a neighbor of A, C, and D. Okay. A is only a neighbor of B. Okay, only a neighbor of B. So you first, let's say you create one of these basic matrix, and then we also row normalize it. So you basically look at how many non-zeros and divide by that. So here you don't have to do anything, but there are 3 neighbors, so each one gets 1/3 of the weight. So this is what's called a row normalized neighborhood matrix. So you can now start bringing in the neighborhood effects in traditional models. So in regression, last time I showed you that in addition to this, you can add the effect of the neighbors. Okay, and this is the spatial autoregression model. But even in other models, you can do that. So if you have, for example, it's interesting, no one brought up Bayesian classifier, which is another popular one in statistics, okay, with Bayes rule. And in this, it basically says a class label at a location only depends on explanatory variable at the same location, and then you write the Bayes rule. But you can bring in the effect of neighbors by saying, class label depends not just on local property but also neighborhood property, right? And you write the Bayes rule. Convolution neural network does already a little bit of that because it takes, right, convolves with the neighborhood. And the idea is bring in the spatial effect. Okay, that's the key. All right, so if you actually apply to this bird nest data set, so this is they had actually tried regression as well as the classical neural network, okay, feed forward one, and their prediction accuracy was down here, but by adding that autocorrelation, they went up about 15 to 20%. This is ROC curve, okay. So at least you are seeing that in data sets, many data sets you would get a bump, okay, not all data sets, but many cases you will get a bump. So that's sort of, a quick story about if you bring spatial effects, it can help you, all right. So what I'm going to do now is to go beyond what we saw in day 1, and I will now talk about how you bring in heterogeneity, okay. So again, the idea here is that if you build even a simple model, whether it's neural network or regression or SVM, instead of building a single model globally for all location, we allow this model to vary over locations. Okay, so that's the idea of heterogeneity. And let's illustrate it with the simplest model, which is regression. So in the traditional regression model, remember the coefficients beta are scalars. But if I generalize it to the heterogeneity, then we are saying that individual betas are location dependent. They are maps. Okay. So here is an example. So suppose, again, this is a toy example. Don't take the model seriously. But let's say crime at a location depends on population and income. This is for hypothetically. In the traditional regression, beta naught, beta 1 and beta 2 would be one number each. Okay. But in geographic weighted regression, notice that beta naught depends on the location. Okay. Here it depends on the location. Okay. And this is again available through many different software that if you want you can try it. Okay. Any quick questions on GWR, how you bring in heterogeneity? Okay. All right. So again, I will give you a few places. Again, the dust has not settled. There are other issues here. So one open issue is how do you actually determine the W matrix? Most of the people take a guess and they say, oh, I want everything within a mile, or 4 neighbors, 8 neighbors, and they will try different W matrix. But one question is, now you have so much data, could you actually estimate W from the data, right? So that's an interesting one. And the scaling I'm going to skip, but let me show one other, which is the interest measure issue. This IID assumption keeps coming back in different form. That's what it's talking about. Okay. So suppose I'm looking at the same bird nest map. Remember, this graduate student went and mapped it, right? So he or she probably saw the nests over here. Then they put a grid on this continuous space, right? And in this grid, this nest ended up being this pixel, right? And that ended up being that pixel, because these are 5 meter by 5 meter area, and nest is 1 feet by 1 feet. So that's what your ground truth looked like. Okay. Now suppose I ran 2 prediction model. I'm not going to name them, but we heard many prediction models, right? And suppose one prediction model predicted nests over here, right? The second prediction model predicted nests over here. So let me first ask you how you would rank these models. So how many of us will favor D? Okay, good. How many will favor C? Okay, maybe one, all right. Now let me turn it around and ask you, how will statistics or spatial statistics rank these 2 models? Okay, why do you think it's same? Why there is a tie in statistics between these two models? Whereas in the room, overwhelmingly, we favored one model, right? So why is it a tie in statistics? Go ahead.
Because both are not predicting the actual outcome. Three incorrect results here also.
Wonderful. So in statistics, your measure of ranking is total square error. You're counting mistakes. How many mistakes in this model? Actually 6 mistakes. You missed the actual ones and you did 3 false positive, 3 true negative. 6 mistakes. How many mistakes here? 6 mistakes, right? Then why we overwhelmingly favor this model when the statisticians don't?
Because spatially it is closer to the value.
Right. So we don't agree with the total square error measure because it's based on IID. Okay, they basically say once you have modeled all the effect, the residual errors is IID, and that's not capturing everything about space. We are not interested in independent pixel. We care about the distance. And if you look at the real phenomena, you know why. The discretization was an approximation to begin with, right? So there are other issues in the space, and people in machine learning and so on, suppose you wanted to change the objective function. How could you look at the distance? What's the mechanism to try to bring it into classical machine learning or statistical model? Anyone remembers? So do we know what regularizer or penalty terms mean? Some of us, right? So in machine learning, they love IID because they want to be fast. Okay, but for them, the way to bring in more domain knowledge is through a regularizer or penalty function. Okay, so you would often see that spatial autocorrelation is used as a regularizer. Okay, that's a way to slide it in. It's not the best way to do autocorrelation, but it's better than not doing it. Okay, the same way, if you want this distance, you can slide it in through regularizer, and chances are you will do better than before. Okay, wonderful. So that's all I wanted to talk about for location prediction. So let's take a quick review and then we go to the break. Okay, we are ready. Okay, what is true, right? Any voting for A? No, it's actually more expensive. Okay, B. All right, good. How about C? Okay, it's actually more general. If you set rho to 0, you get your old model, right? And this, okay, good. So this is a natural place for break. When we come back, we'll look at a couple of more pattern families and some algorithms. And when do we come back? Okay. It's about 11. Okay. All right, so you can maybe
15 minutes.